Okay, in this video we are going to be starting our 10th module. This is going to be our module on fluid statics. This is also going to be the last module that we're going to cover in this Physics 101 course. Okay, so this module, well, in this module we really change gears quite a bit. Pretty much everything that we've been talking about before this point in the course sort of falls under the category of mechanics in physics, right? So we talked about kinematics, we talked about dynamics, we talked about a number of other things. We talked about energy, momentum. All these things are commonly sort of introduced in a course in mechanics in physics, but now we're kind of changing gears to talk about something that we wouldn't normally talk about in a mechanics course. This is sort of an additional topic tied on top of this course, which is fluids. So we're going to talk about fluids in this module. Maybe before I get into the fluids, I'll just mention that. So we've sort of been building up in complexity as we go, right? We started off with 1D kinematics, which was relatively simple. We then amped it up to 2D. And it wasn't sort of a constant increase, but things got a little more complicated. We moved on. We did some work with forces, and then with energy and momentum, and things continuously got more and more sort of complicated and mathematically sophisticated. In this section, we kind of take a step back. The concepts here are not, well, at least the way that we're going to be treating them, are not overly mathematically complicated. So there's a lot of new topics that we're going to be talking about in this section, but they're not overly difficult to use to do calculations with, right? So it should be a fairly sort of relaxed way to finish out the semester and bring us into final seasons here. Okay, so looking at the content that we are going to be covering in this module, we're going to be talking about fluids. We're going to be describing what a fluid is. We're going to be talking about density, pressure. We're going to look at some examples of those two. We're then going to move on to things like Pascal's principle. We're going to look at Archimedes' principle and a few examples of those, and that'll pretty much bring us close to the end of this module and the course. Okay, and so let's get right into it here. I'm going to follow the text fairly closely on this one. So the textbook starts off talking about what a fluid is. I'm not going to go into this too much. I think that we pretty much all have an intuitive understanding of what a fluid would be. But just very quickly, if we think about the common phases of matter, if we think about solids, liquids, and gases, I have this nice diagram from the text just below. We can see sort of the way that these look, right? So we have our solids over here, our liquids here, and our gases over here on the right. Fluids are liquids and gases when we think of these phases of matter in these terms. Okay, so anything where our particles can move freely, as they can in a liquid or in a gas, that's a fluid, or at least that's what we're going to be using as our description of a fluid here. So here I have a few points to remember when we think about these three phases of matter, and we think about fluids. And so solids our particles are locked in this sort of lattice-like structure. Okay, and these are not fluids, right? So this is kind of like our dividing line, right? Like we have fluids here, and not fluids over this way, right? And so solids are not fluids. We have our particles. They're in close contact. They're locked in this lattice-like structure, and our solid cannot easily be deformed, right? So we're not going to worry too much about solids for this, but what we are going to worry about is fluids. And fluids kind of fall into these two categories that we can think of. So liquids or gases. In a liquid, as is also true for in a gas, our particles can move freely, right? So the particles can move around freely. In a liquid, we can usually pour a liquid into a container, and our liquid is not going to escape that container, which is not true for a gas, right? In the case of a gas, we're going to have our gas slowly spilling out of the container. And maybe the most important difference for us is this final difference. Our liquids, generally speaking, are not easily compressed. Okay, so liquids are not something you can easily squish down into a smaller volume, whereas gases are compressible, generally speaking. So gases can much more easily be, you can take a large volume of gas and compress it down into a smaller volume uh, with the same mass, say for example, right? Which you could not do for a liquid. So that's going to be the key sort of difference when we're dealing with liquids and gases as we work through this module. Okay, so I'm going to have the text here open next to me so I can comment on some of the things that they say. They have a little bit of a longer section on the introduction of well, I guess, what is a fluid. Um, but I'm going to leave it there for now. We're going to move on to density here. We have briefly used density before, and I think it's probably something that you guys are relatively comfortable with. But just to restate it here, we have our equation for what density is. Density is mass per unit volume, right? So we have mass over volume here, and that's our density. And so I didn't write it here, but obviously we know that our SI units for mass is kilograms. We know that our SI units for any length is in meters. So a volume is just going to be a meter cubed. So that's going to be cubic meters. And so our densities, our SI units for density will be kilograms per meter cubed, right? And so that's sort of just the equation that we're going to use for density. Let's take a look at a quick example here. I think I have this one directly from the text. Let me look at the text. Oh, maybe I should mention, though, before I get into the example here, that there is a nice table. Yeah, I did mention it here. There's a nice table in the textbook, 11.1. It's table 11.1. In my edition of the textbook, it's on page 392. That has a number of very nice. Well, very nice. I mean, it's basically just a table of different solids, liquids, and gases, and their densities, right? So if ever you need to look up a density, this is a very quick way that you can sort of get a reasonable value for any of the densities you might need. Okay. So now let's move on. Let's take a look at this example. This is exactly the example they have in the text. We're looking at a reservoir that has a surface area. So a reservoir is like a large area that we store water. For example, let's say a city would have water in a large reservoir, and so we're looking at a reservoir here. This reservoir has a surface area of 50 kilometers squared and an average depth of 40 meters, sort of over the whole reservoir, right? And we want to know what's the mass of water held behind the dam that sort of contains this reservoir, right? So we're basically looking at the mass of water held in this volume, which is defined by a surface area of 50 kilometers squared and a depth of 40 meters on average, right? And in the text they have a nice picture of a dam in China here, but we're not going to have the picture here. Let's just concern ourselves sort of with the calculation, right? And so if we wanted to solve a problem like this, what would we do? Well, we know that our density is equal to the mass over the volume, right? But we can also rewrite this if we want just the mass, right? We want the mass here, so we can get mass is equal to density times the volume. It's supposed to be a capital V. And so what's our volume here? Well, our volume is simply going to be our surface area times our height. So this is just going to be, so our V is now going to become our surface area times the height, where the surface area, we're given that surface area, that's our 50 kilometers squared, and the height, we're given that height is 40 meters, right? We also know the density of water. We could look it up in the table. And we would find that is 1 times 10 to the 3 kilograms per meter cubed, right? So what we end up doing is we end up wanting to calculate, well, the way they do it in the text is they calculate this V first. So we know that V is equal to AH, and they simply write down the 50 kilometers squared. We want to get this into square meters, so we can turn it into cubic meters eventually, right? And so to get it into square meters, we need to take, we have 10 to the 3 meters per kilometer, right? This is per 1 kilometer. And we're squaring this, right? Because we have square kilometers here. This is just us getting from the units of square kilometers to square meters. And then we're going to multiply this whole thing by 40 meters, okay? And if we do that calculation, we're going to find that we have about 2 times 10 to the 9 meters cubed of water here, okay? And so with that value, we can now substitute this V back into our equation here, and we have M, our mass, is equal to our density times our volume. Well, our density, like I just mentioned, is going to be 1 times 10 to the 3 kilograms per meter cubed. And maybe I'll put this in brackets. And this is going to be multiplied by the volume that we just calculated, which is 2 times 10 to the 9 meters cubed. So these meters cubed are going to cancel, and we're going to end up with a mass in kilograms, which is what we're looking for. And if we do that calculation, we're going to find that the mass of water contained here is 2 times 10 to the 12 kilograms of water. Okay, so that's the answer to what the mass of water behind this dam is. Okay, and so fairly straightforward, right? We just have the one equation. There's not a whole lot that we would want to do with it here. This is a pretty straightforward example. So we have our value, and we can sort of move on to the next idea here. Okay, so the next thing that the book talks about, the next thing that's logical to talk about in fluid statics is pressure. And so we haven't really talked about pressure before, so this is a new definition for us. And pressure. And I've mislabeled it here, so this should not read density. This should read pressure. So pressure, capital P, is the force applied per unit area. Okay, and so pressure is defined by the equation that we have down here in this box. Pressure is just force over the area which it's applied to. Okay, and the SI units for pressure are called pascals or pascals. And so they do get this sort of special unit to them, right? PA, we give it this symbol PA, and 1 Pascal is 1 Newton per meter squared, right? And it has the units you would expect because our areas are going to have meters squared and our forces are going to have newtons, so we expect to see newtons per meter squared, and that is what 1 Pascal is, okay? And so maybe the best way to get a handle on this is to again look at an example here. So let's do that. This is again an example directly from the text. We're looking at example 11.2 here. And what are we trying to answer? We're trying to look at, so we have an astronaut is working outside of the International Space Station where the atmospheric pressure is basically 0, right? So we have the astronaut out in space. They're wearing an air tank so that they can breathe, right? The pressure gauge on the air tank reads 6.9 times 10 to the 6 pascals. And so what force does the air inside the tank exert on the flat end of the cylindrical tank? Okay, so the cylindrical tank has a diameter. So we're imagining somebody in space, right? And they have an air tank on their back. That's my air tank. If we look at the air tank, let's say it's a cylinder, looks something like this. This is sort of blown up image of it, right? And we're told that the diameter of our cylinder, so this distance in here, this is going to be 0.15 meters, okay? And we're also told that the pressure inside this tank is 6.9 times 10 to the 6 pascals, okay? All right, and so we want to find the force that is experienced by let's say this interface. What's the force exerted on this this end of the cylindrical tank? Okay, and so right away we can just go back to our equation. We have P equals F over A. Well, we're looking for F, so P equals F over A. We can isolate the F. We end up with F is equal to PA. And right away, it's a pretty sort of straightforward calculation. We know that the area of our the end of our cylinder here can be written as pi r squared, right? So it's going to end up being the pressure times pi r squared. We have to be careful a little bit because we're given the diameter. So if d is equal to 0.15 meters, well, this means that r is going to be equal to half of that, so 0.075 meters. And then we just have to substitute these numbers in. So we end up with f. Again, maybe I'll just rewrite it here. P pi r squared. We have our p, 6.9 times 10 to the 6. We have pi, 3.14. And we have our r, 0.075 meters. If we do that calculation, we're going to end up finding a value of 1.22 times 10 to the 5 newtons for the force on the end of this cylinder. Okay, so that's our answer for that question. Okay, so that's one example of a force exerted by air here on our cylinder. And this is just an example of us using this idea of pressure, this equation for pressure written in terms of a force over an area. Okay, so we then move on and we look at the variation of pressure with the depth of a fluid. Okay, so this is now corresponding to section 11.4 in the textbook, and it starts off with a sort of derivation of what's going to turn out to be a fairly general equation. It does it in a sort of specific way, so we're looking at the variation of pressure with the depth in a fluid. We're going to find an equation for it by doing a very specific calculation on this cylinder of fluid here, but we're going to find that the result that we find is widely applicable. It's not only going to work for this one cylindrical case that we're looking at here, but the equation is going to be an equation that we can apply to the pressure that we find at sort of any depth in any fluid, which we're going to find is not easily compressed. Okay, and I'll talk about that maybe a little bit more in a second, but let's start off with the sort of example here. Okay, so we're looking at variation of pressure with depth in a fluid, and so we're going to find that the pressure exerted on any object which is in a fluid is going to depend on the depth that object is in the fluid. So obviously the deeper you go, the more pressure you're experiencing by the fluid above you, right? And so we sort of experience this all the time, right? When we live at ground level, at sea level, we experience the pressure of the atmosphere above us, right? So all day long, every day, we have the pressure of the atmosphere pushing down on us. We can also see it sort of much more dramatically because every day in this atmospheric pressure, our pressure is not changing, so we're used to the atmospheric pressure around us. But if you dive into a pool and you swim down very quickly, you can feel the pressure of the pool water pushing down on you quite quickly as your ears start to pop or whatever. As you dive deeper, you can feel that pressure right away, right? So let's take a look at sort of how we could derive an equation to describe what's sort of going on as we go deeper in this fluid. Okay, so let's consider the container shown below here. This nice clear glass container here with a bunch of fluid in it. I guess it could be water. This is directly from Figure 11.9 in the text. So the bottom of this cylindrical container here, this thing that we have labeled A, this bottom, we want to calculate the pressure exerted on the bottom of this by the weight of the fluid above it, right? So the weight again is just the force of gravity acting on all this fluid. So this is just Fg equals W equals mg, right? And so they've written these as bold values for G and W, which are vectors, right? And we've seen this throughout the text, sort of used repeatedly, right? Okay, so we want to calculate this pressure on the circular area below, right? So we can start off by writing our equation for pressure. We know that pressure is just a force over an area. But we know that in this case, our force is just mg, right? So that's just going to be mg over a, okay? But we need to find the mass of this column of liquid or fluid, I guess, in principle, but in this case, liquid above. But we know that we can find this mass from our density times the volume that we have, right? That's kind of an ugly V. There we go. Okay, and we know that our volume is simply going to be our area times our height, right? So whatever the area of that disk is times the height is going to give us our volume. So that's just going to be rho area height. Okay, and we'll leave it in those terms here for a minute, which will let us to which will lead us to a cancellation that we can make in a moment that'll kind of clean things up. So let me just label this like this, and let's substitute this back into our pressure equation here. So we have P equals mg over A, but we just saw that M is equal to rho AH. We still have that G on top, we have an A on the bottom. These A's will cancel, and this gives us P is equal to rho HG, right? And so now we have this expression for the pressure exerted at the bottom of this cylinder by all the fluid above it. But we're going to find that even though we've derived it in this very sort of specific case, this equation is widely applicable. Okay, so this is the equation that's going to give us the pressure experienced by any object in some fluid of density rho at some depth h in our Earth's gravitational field, right? And this is going to be applicable to not just the bottom of the container, but any object in there. And really, we're going to find that this will work for any fluid, so long as the density of the fluid doesn't change significantly as H increases, right? So as long as we're dealing with, say, water, for example, which has a density that's equal at the close to the surface as it is deep in the water, because water is not easily compressed, well, this equation will work. This equation wouldn't work so well if we were dealing with a gas that's easily compressed, right? Because as we get to the very, let's say with our atmosphere, so this wouldn't work great over large distances through our atmosphere in an up and down direction, right? Because at the very top of our atmosphere, as we move further and further up, the air is less and less dense because there's less air on top of it compressing it down, right? And we talked about how gases are more easily compressed. So as we move down over larger and larger H, then our rho is changing, and that means that this equation is no longer valid if rho changes significantly over the H that we're interested in, okay? But this is a good equation to keep in mind, so I've boxed it off here. And again, just to restate it one more time, this is the pressure that any object is experiencing at some depth h for some fluid of density rho with g acting on it, right? On our planet's surface or whatever, right? So we need to have g there for it to sort of make sense, okay? And so we'll keep that equation in mind, and we're going to do an example with that equation in mind here. So again, this is an example directly from the text. We're kind of working with the same sort of reservoir that we talked about in the first example we did in this video. This is example 11.3 from the text, and we're calculating the average pressure and force exerted by all this water on the dam, which is sort of keeping this reservoir sort of at bay, right? So we're now going to consider the pressure and force acting on the dam that's sort of retaining this water. We see it in this figure here, and let's think about what we have here. We can imagine this would be some large reservoir, and this is just a dam holding one end of it up, right? This is all the water here, and this is our dam. Our dam is going to have a width here of 500 meters. And the water depth, the full depth here is 80 meters at the dam, okay? So earlier we said a 40-meter average depth, but at the dam we have this 80-meter depth or average depth over this 500-meter width, okay? And in part A, we want to calculate the average pressure on the dam due to the water. And in part B, we want to calculate the force exerted against the dam and compare it to the weight of the water that we calculated in 11.1. Okay, so I think I ran out of space, right? So I'm going to do it on this next page here. And again, this is going to be very, very close to what the textbook talks about here. And so, what's our plan going to be here? Well, our average pressure. So we're looking for the average pressure exerted on the dam. Now the pressure won't be exactly equal at any point on the dam, right? If you're very, very close to the surface here, there's not a lot of water over you, so there's not a lot of pressure acting on the edge of the dam. But if you're very, very far down, there'll be more. We're looking for the average pressure, right? And so what does it mean to find the average pressure here? Well, that means to find the pressure, the average pressure, at the average depth that we're going to be at, times the density of water times our gravitational acceleration. Okay, and so we're looking for p bar or p average, and so they nicely give us this this sort of drawing here where they give us our h bar. This is sort of the full h over 2. So we can think of h bar as the average depth, right? And so really it's going to end up being just h over 2, okay? And so that's going to be our 80 meters over 2, so that's going to be 40 meters. And so we can do the calculation right here. We're going to end up with 40 meters. We need the density of water. We know that that's 1,000 kilograms per meter cubed. Okay, and we have our gravitational acceleration, 9.8 meters per second squared, right? So if we do this calculation, we're going to end up finding that we have a p bar equal to 3.92 times 10 to the 5th, and it's going to end up being, you can kind of see it from the units here, you're going to have some cancellation of these meters. You're going to have some seconds squared left over, kilograms. In the end, it's going to work out to being newtons per meter squared, just as we expected. And this ends up being written in pascals. We can write this as 3.92 times 10 to the 5 pascals. Or the textbook also then cleans this up a little bit and writes this in terms of kilopascals. I'm not so interested in worrying about that kind of sort of prefix on our units here. We could write this as 392 kilopascals, but I wouldn't worry about that. This would suffice as an answer for sure. Okay, so just remember that pascals are newtons per meter squared, and we're kind of good to go from there, right? And in part B, what are we looking for in part B? We're looking for calculate the force exerted against the dam and compare it to the force of the weight of the water that we calculated in the previous example. So we were supposed to have found 1.96 times 10 to the 13 newtons. So let's just remember 1.9, what was it? 1.96 times 10 to the 13 newtons. That was the force of gravity sort of acting on all that water, right? So that was the force, that was sort of the gravitational acceleration times the mass giving us this weight of the water, right? So here we're going to end up with the force exerted on the dam by the water. That's what we're looking for here in part B. We're going to compare it to this value afterward. Well, that's just going to be equal to our average pressure times the area over which it's exerted, right? And we can remember that if I scroll up here a little bit, we have our expression for pressure as it relates to force and area. So if we're looking for force, that's just going to be PA, which is what we have down here. And I have the numbers here from the textbook, right? So we just found our average pressure, right? So we're going to use that number. We know that our area is going to end up being the 80 meters of the sort of depth of the dam times the 500 meters of the width of the dam that we're looking at. And so this is going to come out to be 4 times 10 to the 4 meters squared, and this should be a 4. Okay. And so right away we can sort of jump right in and get our force. Our force is simply going to be this value for p bar, or our average p. It's going to be 3.92 times 10 to the 5, and now it's times our area, which we just calculated, so that's times 4 times 10 to the 4. And if you do that calculation, you're going to find that F is equal to 1.57 times 10 to the 10 newtons. Okay, so this was the full weight of the water, and this is the force exerted by the water on that area of the sort of surface area of the dam which is facing the water, right? So we can see it's significantly less, 3 orders of magnitude, and that's because not all of the weight of the water is supported by the dam, right? A lot of the weight of the water is pushing down against the bottom of the reservoir or the shores or whatever, right? And so this would constitute an answer to part B here. Okay, so we're probably going to leave this here. There may only be 1 or 2 more videos in this module. Like I said, we're going to look at Pascal's principle. We're going to look at Archimedes' principle. But after that, we'll be pretty much done with most of the topics that I'm interested in this section, and that will sort of wrap up the course. Okay? All right, I'll see you guys in the next one.